Hello, and I apologize for the unorthodox recording area. So today we are going to talk about algorithm efficiency and big O notation. So those are what the next series of videos are going to be about. They're going to be about costs and evaluating what the cost of your algorithms. All right. So let's talk about why we need this first. I'll just boot up Guinea for a basic text editor. Right, and let's go ahead and close all these other guys up. We don't need them anymore. Okay. All right. So you're running a program has certain costs associated with it, just naturally. We're going to use up some resources. So right now, let's start our discussion of what are the resources we can use. What are the resources that are available to us? All right. So there's a couple of them that stand out, so take a moment to think. What are resources that our programs use? And so you can pause the video here and think about it. You didn't pause, but that's okay. So I'll go ahead and tell you anyway. So one of the most common resource is time. Our programs use up time. And this is the one will be, so this one, by far, of these costs is the most important, and we'll get to why. Okay. Another resource cost that programs can use, another resource that they can take up, is space. Right. Let me show you. System monitor. Right. I can open up this thing. Right here I am, and it says that I am using 3.5 gigabytes. My program is using up space. Right. My operating system here is using up space for my computer. Okay, so space. And that used to be a lot more important, and it still quite is, but we'll get into that. And another one that's come up a lot more these days is the cost of energy. Energy is another big cost these days. And the reason for that is that we're all carrying around these little things, right? These, what you would call in the 1970s a supercomputer. And extremely so, and the reason I can carry it around in my pocket is because it has a battery in it. Now the battery, of course, it gets expended when the processor says, "Hey, I need some power to do some computations." So an algorithm that takes up less energy means that it's going to impact your battery life and make your essentially you can use your portable computer longer. So of these, time is the most important. And why is that? Well, the reason is that you can buy extra space. You can always buy more RAM, you can buy some more stuff. You can always buy more hard disks, you can buy space. You can always buy more energy. You can get more energy. There's always more energy available. Time, on the other hand, you cannot buy. You cannot buy time at all. You cannot go into your local supermarket and pick up 10 seconds. Time is the most valuable resource. You should treasure it. And that's also, and on a more practical note rather than a philosophical one, the reason time is important is because that, it takes about 3 seconds for a person to get fed up with a web page loading. Once those 3 seconds are up, the person's probably going to get bored and go something else. We've become very accustomed to being very impatient with our computer usage. So we expect things to load, and we expect programs to load quickly. Also, some problems, the algorithms for them are just, they can't go there's a limit to how fast they can go. Like the traveling salesperson problem, at a certain size, that problem will take centuries or more to solve. All right. So, what we're going to learn over the course of the next couple videos are ways we can evaluate this. Now, part of the issue with evaluating how fast an algorithm runs is that my computer will run very differently than yours. I've got a nice processor here, but it's nowhere at the speed of a modern desktop processor, right? But and it's certainly not going to be anything like the processors that are coming out in a couple of years, right? So the question becomes of like, how do we evaluate this in a way that's agnostic to the hardware, right? So the way we do that is we view computers essentially as identical machines. They have, they have unlimited space and unlimited time to solve a problem, and their speed, you can just set, every computer runs at the same speed for the purposes of our evaluation. But now that's when we get into big O notation, right? Here I'm going to be running some algorithms, and you're going to see some differences in time, right? So what we're going to learn about is some of the basic big O notations that express how quickly an algorithm runs. We're going to learn about O of 1 speed, also known as constant time, what algorithms are constant time and what that means, what it means for an algorithm to be O of n time or a linear time algorithm, and what it means to be for an O of n squared algorithm or a quadratic time algorithm. And these are just all various speeds that we can run at. So, and I'm going to illustrate this with some examples. But we're going to be now these measurements can be used on any of these, but we're going to be evaluating this in terms of time. So rather than a constant time, we can just simply say linear, constant, or quadratic. And we just switch that to time if we're talking about time, space if we're talking about space. Okay. So, without further ado, I'll get started with this in the next video.